The market is sometimes likened to an invisible hand that coordinates the actions of participants who may never communicate or make physical contact with each other. Outside of price theory, the teaching of causal inference generally lacks a market-oriented framework for analyzing treatment effects. Here we argue that the reality of market mechanisms can be embraced rather than assumed away. Indeed, a treatment control framework comes straight from old-school economic theory. It helps interpret treatment effects and apply them to situations other than the ones where the measurement occurred. In a market, the outcome for any one participant depends on what is happening with the other market participants. You might say that the invisible hand creates spillovers in the econometric sense. Of course, econometrics has simultaneous equations, particularly that the quantity supplied must equal the quantity demanded. But that is beside our point. Markets also coordinate buyers with other buyers, even those who never meet or communicate with each other. Same on the seller side. We will show that the invisible hand effects are easy to deal with. We begin with a simple example to show how much is at stake. Treatment effects can easily have the wrong sign. Then we'll generalize that example to encompass the standard demand theory setup. As entries in a substitution matrix, treatment effects are a weighted average of scale and substitution effects. The Hicks-Marshall characterization works far beyond demand theory applications. It does not need optimization or anything like that. All it needs is a weak concept of comparability between the treated and controls. From there, we can see how to take observations from a targeted treatment and scale them for a counterfactual of a broader treatment. Market frictions make that possible. Here's the simple example. We have an industry with a bunch of producers. Each provides a fixed quantity of inputs. The treatment is to increase the productivity of those inputs. Maybe these are farmers with fixed land and labor, and an experimenter will give them fertilizer or teach them something. Maybe these are office workers who will be given some awesome AI tool. Some of the producers are put in a treatment group. The others are left out. We call this a targeted treatment. What will this targeted treatment tell us about the consequences of another experiment that differs only in that it treats all producers instead of some of them? Looking at the targeted treatment, the industry quantity goes up and the price falls. Treating the entire market will, of course, change quantity and price even more than the targeted treatment does. Now let's view these same two experiments at the firm level. Firm quantity is now on the horizontal axis. Revenue in this picture is an area. To simplify the picture, we assume that the treated and the controls have the same output and revenue in the baseline. Here's the treated. They're more productive, of course. What if, for a revenue outcome, we estimated a treatment effect as the difference between treated and controls revenue? In this picture, it's the area R4 plus R6. It is also the difference in differences. More specifically, the difference between the average revenue change of the treated suppliers and the average change for those untreated, because the two types of suppliers have the same revenue in the baseline. Throughout this video, we refer to did and treatment effect interchangeably. But that's not the effect of the treatment on the treated, because the treated lost the area R1. So did the controls for that matter. Therefore, the treatment effect on the treated, TOT, is strictly less than the did. The TOT could have the opposite sign. Now let's look at market-wide treatment. Price falls even further. The controls are contaminated. But the contamination is a big part of what we want to know. We call the effect of the market-wide treatment epsilon or a scale effect. This is yet a third number, namely R6 minus the two green areas. It can have the opposite sign of did. Indeed, it will if industry demand is price inelastic. A quite general result is that the scale effect is outside the range spanned by did and TOT. What we cannot say in general is whether scale and did have the same sign. This is figure 1 again. I want to address spillovers in this context. You might think that spillovers can be safely ignored when we treat just a tiny fraction of suppliers. There would be no noticeable effect on the average supplier among the controls. That's correct, but a disadvantage of a small targeted treatment, not an advantage. A market-wide treatment has lots of spillovers. Every treated supplier is experiencing a myriad of spillovers from those other suppliers, who are also treated. Market spillovers are of intrinsic interest. Any technique that makes the spillovers disappear is missing some important economics. When we reduce the extent of the targeted treatment, it moves E prime toward the baseline and away from E double prime. Even more extrapolation from the targeted treatment is needed to learn about the market-wide treatment. Now we focus on experiments that intend to learn about features of demand. It does so by treating supply, which is the right approach in principle. Let's generalize the simple treatment control example to relax the assumption that the suppliers are producing perfect substitutes. Now we have exactly the industry model from Chapter 11. That model had two factors that were imperfect substitutes in a constant returns production function. We call them L and K in that chapter, although in a second we'll replace L with the letter T to help us remember that we refer to treatments. Output is Y, which must coincide with the quantity demanded at the equilibrium price P. Recall that the second equation connects industry revenue PY with the combined income of the two production factors. The final two equations say that the equilibrium factor quantities minimize production costs. All we have done here is to change some of the lettering to better match our discussion of treatments and controls. Lowercase t and k are prices. Uppercase T and K are quantities. Let's use the Hicks-Marshall laws that we derived in Chapter 11. Recall that we used capital delta to indicate log changes. Our first result is that the treatment effect is just negative sigma. It has nothing to do with the expenditure share of the treated or the controls. It has nothing to do with the scale effect. Our next result is that the tot is a share-weighted average of scale and did. Sigma and epsilon are the two foundations on which many tots can be built, depending on the share. As we increase the share treated, E prime moves away from the baseline and toward E double prime. The third result is that the market-wide treatment reveals the price elasticity of demand. It has nothing to do with substitution between T and K. Here is the full substitution matrix. The diagonal is the own price elasticities of demand. The off-diagonal elements are the cross-price elasticities. In econometrics terms, those are the spillovers. The spillovers are irrelevant for connecting the treatment effect to preferences. The treatment effect is just sigma, regardless how much spillover there is. The treated also experience spillovers. So when we have a larger treatment share, that means a greater spillover for everybody. It gets differenced out in the treatment effect. Our metric of spillovers is the sum of the off-diagonal, which works out to scale minus treatment effect. Most of this can be done without demand theory or without maximization. That is, the outcomes do not have to be prices or quantities. The treatments do not have to be prices or quantities. We could be talking about mortality or test scores or any number of other things. The proof is in our paper, but the only assumption needed is that the T and K are comparable in that treating them both equally will not affect the gap between their outcomes. We looked at quantity outcomes from price treatments. To have price outcomes from quantity treatments, which is more like our figure 1, invert the treatment effects matrix. The algebra of this inversion is clean due to the Hicks-Marshall structure. The weights stay the same, and we just replace epsilon with its reciprocal and sigma with its reciprocal. For figure 1, which assumed perfect substitutes, the sigma terms disappear because sigma is so large. That is, quantity treatments do not change the ratio of the two prices. Because it has price as the outcome, this expression helps in the study of wages, which are prices in the labor market. Let's look at a few wage determination examples. The first is the union wage effect. The union is going to restrict the supply of labor to its part of the economy in order to increase wages there. The workers unable to be in that sector go to the other sector. That means delta T is negative. Delta K is positive and proportional to delta T because the non-union sector is absorbing the reduced T sector labor. The proportion is the relative shares of the two sectors. Local to a zero non-union premium, there is no aggregate output effect. That is the second-order property we saw in the excess burden chapter. These are the two expressions for the log wage effects in the two sectors. They have only the substitution effect. Union wages go up and non-union wages go down. The union wage increase is the treatment effect on the treated or taught. Here is the DID, which is the estimator commonly used in the literature on union wage effects. It exaggerates the taught due to the negative effect on non-union wages. This got a lot of attention in the early union wage literature, but not so much anymore. Let's look at the link between wages and productivity. From an input perspective, barbers today cut hair almost exactly as they did in the first half of the 20th century. A chair, mirror, scissors, and sink. By all accounts, fully scheduled barbers have hardly changed the number of haircuts they perform per hour. Meanwhile, other occupations have experienced dramatic productivity growth over the same time frame. For example, the number of bushels of corn produced per farmer has increased by an order of magnitude. Let me tell you that the real wage changes were large, but essentially the same for the two occupations. The DID for a wage outcome is 0. Should we conclude that productivity has no effect on real wages? You might want to pause the video to think about answers to the puzzle. You might say there are other things going on, which is not wrong but unnecessarily vague. Farmers and barbers are in the same market. They have a choice of occupation. Real wage growth in barbering largely depends on productivity growth in all of the other occupations rather than barber productivity growth. In markets, assuming that treatment effects are isolated to the treated is a poor approximation. The invisible hand spillovers are no small issue. They are the main event. Essentially, all of the barber's wage gains come from productivity growth outside their occupation. What do treatment control comparisons, such as difference in differences, show? One thing we have already pointed to, a treatment control substitution effect. It shows the individual consequences of being selected for the treatment rather than the control. Remember the Vietnam draft lottery. A treatment effect is informative about the value of a favorable draft number. If the control is contaminated, we want to count that because it is part of the opportunity cost of being treated. But the treatment effect of a targeted treatment is not the consequence of treating the entire market. This last point is a negative one. Perhaps it's the low point of the video, but we will add optimism before ending it. Difference in difference estimators will always include a treatment control substitution effect, but with market frictions they can also include a bit of the scale effect. Understanding those frictions allows inferring the part that is scale. This is a non-exhaustive list of approaches to market frictions. One is to say that some of the controls are out of the market. The second is to put a porous barrier between two markets, so that their prices are linked, but imperfectly. A third is the Salop or Circle City model, where market spillovers diminish with distance. In all of these cases, a targeted treatment's DID and TOT are enough to recover the scale effect. The scale effect is outside the range spanned by DID and TOT. Let's begin with the question of cigarette tax incidence. The treatment is a cost change, namely a tax increase. The outcomes are retail prices, inclusive of the tax. We ignore the market frictions for a moment, because ultimately they are not so important for understanding pass-through. We will bring in frictions on the next slide, primarily to illustrate possible relationships between treatment effects and scale effects. Think of the retail price in a state as the sum of a national wholesale price and a state-specific excise tax. In fact, for many years, even the largest cigarette manufacturers had only one wholesale price for the entire nation, despite vast differences in taxes and other market conditions across states. Why wouldn't these manufacturers' wholesale price discriminate across states? You might want to pause the video to think about answers to the puzzle. Cigarettes carry a lot of value per pound. It would be profitable for a wholesaler to get a truck, driver, and fuel in order to make his purchase through another state's wholesaler who gets the lower price. So the manufacturer might as well offer all wholesalers the same price, rather than make them go through the transshipping hassle. It's a different story for consumers, each of which deals in far smaller quantities. The difference in differences takes out any wholesale price effect. In the real world, National excise taxes increase retail prices 40% more than the DID suggests because the wholesale price goes up too. This is an equilibrium spillover. Let's analyze this formally, allowing for possible market frictions. It's a two-area model. Outcomes are retail prices. Treatments are area-specific excise taxes. Here's profits for the manufacturer. Tau is the relative size of the T area. Both areas have the same per capita demand curve, but different retail prices. I'm coloring the wholesale prices. The profit from an area depends on the wholesale price in that area, which is the difference between the retail price and the excise tax. There is an additional cost of tolerating different wholesale prices in the two regions. This cost is where the market frictions come in. If it were convex enough, then wholesale prices would be identical across regions, as on the previous slide. Otherwise, there will be some wholesale price discrimination. The market spillovers across between will be less than within areas. We calculate first-order conditions, not shown in this slide, and calculate comparative statics with respect to the two excise tax rates. We refer to the scale effect as ρ because it's the national pass-through rate. It is the usual pass-through parameter coming from the second derivative properties of the demand curve. The DID is no longer just one, as we had without market frictions. It also brings in a bit of the scale effect. The weight on the scale effect depends on the intensity of the friction, which is represented by the second derivative of the C function. We could do another video on this, but here just briefly point out what can be done when the market spillovers diminish with distance. The model has producers evenly spaced around a circle. Here we have 8, but it could be any number bigger than 1. A targeted treatment here will be administered to 1. I colored that one in red. Market spillovers will be experienced by the others. The outcomes are the prices charged by the producers. The treatment is a production cost shock. The second equation for TOT is the same one we had before. It still holds. But the special result for the Salop model is that the scale effect is the sum of the DID and TOT. In a sense, they are both DIDs, but with our DID variable using the adjacent neighbors as comparisons, whereas the TOT uses the producer on the opposite side of the circle for comparison. The special case obeys the more general principle we said, which is that the scale effect is outside the range spanned by DID and TOT. A key lesson here is to acknowledge trade and put it at the center of the analysis. This video is unique in economics to emphasize trade in discussing causal inference. Other chapters of Chicago price theory are unusual to emphasize trade for the purpose of understanding price controls, antitrust policy, and externalities. Each of these chapters is built on our industry model from Chapter 11. A second point is that we push back against the perception that externalities are the primary reason why there would be indirect effects of treatments. Finally, difference in differences and related methods reveal substitution effects, not scale effects. This presentation can be viewed as a research paper at did.chicagopricetheory.com.